To solve this complex differential equation, we're first going to integrate, and then we're going to use a series of identities to simplify the equation. So first, let's get this in terms of w with respect to z. To do that, we would integrate m over 2 pi z minus a dz. So this would then become m over 2 pi, which we can just pull out, so it looks like 1 over z minus a, which becomes ln z minus a plus c. We know this because the integration of 1 over x, which is a reciprocal, is ln x. So 1 over z minus a is just ln z minus a. Then we have a common identity, which is z equals x plus iy. We can use this to change this so that it's in terms of x and y instead of with z. And we know that z minus a would equal x plus x minus a plus iy. So z minus a would equal x minus a plus iy, which is the equivalent to the real term multiplied by the exponential to the power of I theta, where r is the magnitude of z minus a, which is, if you want to find the magnitude, you square each term and then square root the whole thing. So that's just going to be x minus a all squared plus y squared all square rooted. And then if we define what theta is, you're going to have theta equals arg z minus a, which is the inverse of tan y over x minus a. So there's a lot of identities here that you either have to remember or you'll be given, but now we're in a position where we can start substituting in to get this in terms of x and y. So the next steps is to substitute everything here. So we have ln z minus a, and that's going to equal ln r plus I theta, which is going to equal, I'll put it down here, ln x minus a squared plus y squared, all square rooted, plus I, the inverse of tan, y over x minus a. We know that ln u, which is all square rooted, is the same as ln u to the power of a half, which is equal to a half ln u. Tons of identities that we're having to remember. So we can now clean this bit up. So you're going to have half ln x minus a squared plus y squared plus I, and then it's the same as above, inverse of tan y over x minus a. But we have another identity, which is w equals u minus iv. This is where the u part is the real part and the v part is the imaginary part. So we know that if this is w equals, this part is real, and this part from here to here is imaginary. So it doesn't include the I. So we've now been able to solve this complex differential equation and represent it in its real and imaginary part using identities.